Thanks, Eleni. Thanks, Joe, for inviting me, and thanks everyone for waking up to come to the talk. I'm sorry, it's a really weird title, and it's really because I was too embarrassed to send Eleni and Joe my real title, which is just some research directions that I think are interesting, and maybe you will too. I think the context for this is that machine learning has changed a lot in the past couple of years. That's maybe a huge understatement. And I've seen a couple of research directions sort of, emerge a little bit more on the horizon of what people are looking at. And I think these are really interesting. And I haven't seen too much work in the sort of differential privacy community that sort of look into these things as well. So that I'm basically going to just be chunking this into 3 different chunks. I want to talk about training data attribution, data curation, and sort of alternative privacy semantics that people have been looking into in the sort of DP adjacent world. And I'm going to be not talking about, like, I've done sort of some work in each of these areas, but I'm not going to be specifically talking about, papers that I wrote except when appropriate. And so I'm going to be referencing a lot of stuff. And my intent is that sort of none of this is maybe not everyone in the room will have seen all of these papers. And so I wanted to sort of make sure that you're not sort of like scribbling down furiously if you find one of these directions interesting. And so you can actually go to, I made like a little website that sort of is basically a summary of the talk and includes like all of the references and like open questions that I'm going to be talking about. At TPDP last year, I think the room was a lot deeper than it was wide. And so I'm glad that no one is going to have to sort of run to the front of the room here to get a picture of the QR code. This is not the last time the QR code will be up. It'll be sort of throughout the talk, you'll be able to access this if you're not actually that interested now. It's also on the webpage, yeah. And the QR or the URL is right below it. There's no tracking or anything happening. And I think I've managed to filibuster enough time for people to actually take a picture if they're interested right now. And if I haven't gotten your interest, maybe at some point you'll want to get the QR code. But so basically what I'm going to be doing is as sort of throughout the talk, I want to like introduce these areas a little bit briefly, and then try and convince you why someone in the DP community might be interested in these as well. So I'm just going to jump into training data attribution. This is like, out of the 3 that I'm going to be talking about, this is my personal favorite. It's sort of been really top of my mind recently. And to start, you need to have this sort of caricature of machine learning. You have your big training data set. You run your complicated machine learning algorithm on it, and you produce your big model. And sort of the goal of training data attribution is when you're provided with an input and sort of output from this model, you want to be able to connect that output back to some training example that was sort of highly influential for producing that output. And kind of what you can think of this as like is if you hadn't used this training example at all, that output would be really different. And I want to sort of connect this to the DP world through one of my favorite papers of all time. Does Learning Require Memorization by Vitaly Feldman. This is a classic. What's really interesting is if you sort of look at some of the follow-up work from this paper, it's led to really nice improvements towards like membership inference attacks, which are of big relevance here, and also the training data attribution community. There's sort of direct connections there. And I kind of want to try and give you a sense for why I think that's the case. But first, I have to give you like a short explanation of what this paper does. It's a sort of theoretical paper that proposes this idea of subpopulations in training data sets. So you can see here, this toy data set has 3 subpopulations in it. There's these blue pluses, these green minuses, and then there's this random subpopulation out to the right that's this red circle. And we want to know if that red circle is a plus or a minus. And right now, we don't have enough information to make that decision. It could just easily be a minus as a plus. But the second that we see this other example, this training example that's just green minus here, we really know, we have a very high confidence that this is going to be a green minus. And so that's the extent of the depth that I'm going to go in here. But you can see that this is telling a story about memorization. you need to sort of memorize this green minus in order to do well on this subpopulation. And it's also a story about attribution. If you'd not seen this green minus, you wouldn't be able to do well on this red circle. And so this green minus is heavily influencing the prediction on that test point. And what's cool about this paper is, then Vitali and the co-author Qian Zhang, they tried to understand, is this something that's actually happening in like practice when we train machine learning models? And what they did is, instead of trying to go through all these training examples and see, is this a subpopulation, remove it and retrain without it, what they did is they did something a lot more efficient. And they trained a bunch of models on like different halves of the data. So this is a nice technique. And basically, you can see here, like model 1 is trained on some random half of the data. Model 2 is on some other half, and 3, and you keep going and going. And what you get out of this is something pretty cool. Basically, you're going to get, for any training example, which is a sort of row here, you're going to find that some of the models have trained with it, and some of the models have trained without it. And so by comparing the behavior, you can start to answer questions about memorization and attribution like they did. And some cool things, like nice qualitative things that you can find as a result of doing this analysis is you can find some images that are heavily memorized in ImageNet. So for example, this rain barrel on the top left, the models that contain it are really good at predicting that it's a rain barrel, but the models that don't contain it, that have never seen that example, are really bad at predicting that it's a rain barrel. And what's interesting is you can see this example on the right. This test example is also a rain barrel. And if you haven't seen the rain barrel on the left in your training set, my directions are wrong, but if you haven't seen the rain barrel on the left in your training set, you're really bad at predicting this rain barrel in your test set as well. And the same sort of story for the carpenter's kit and the dam down below. And so you can see here that this is like an empirical evaluation kind of these memorization and influence questions that sort of came up a little bit in this long tail paper. But then what's really cool is that this sort of directly led to, this paper directly led to some really nice advances in membership inference and in training data attribution. So this is a slide from Nicholas Carlini's talk on membership inference from first principles. If you've heard of the Lyra membership inference attack, this is the paper that introduces that. And what you can see is sort of in his slides from the talk when he presented it, directly references Feldman and Zhang. And he has exactly this, 50-50 picture in his head when he's talking about this. And you end up with these two models, these two sets of models, just like they did in their work. And of course, there are more tricks that go into making this like a really state-of-the-art membership inference attack. But it's very cool to me that this sort of directly follows from this work. And another thing that directly follows from it is some really cool recent work on training data attribution, known as sort of data models. These are slides that I ripped from a recent ICML tutorial on training data attribution. That was really nice. This tutorial is linked in the talk notes, and it's a really good sort of primer on training data attribution. But there's this idea of data models, which I'm not going to go too much into, but you can see that it derives, they sort of use this 50-50 subsampling idea as well, in order to sort of understand attribution better. What's also very cool is that in the their first experiments in this paper, this training data attribution paper, they actually used exactly the models that Feldman and Zhang trained and open sourced in order to run their preliminary experiments. So there's really, really deep, direct connections back to this earlier work that was motivated by like differential privacy and memorization. And I'm gonna try and give you maybe like a little high-level understanding, intuition that sort of is in my head for why I think these areas are actually somewhat related. In differential privacy, right, we're very accustomed to thinking about these two adjacent databases and the sort of distributions that your training algorithm produces when you run it on these databases. In differential privacy, like we have the for all statements about the output set and the two all sort of adjacent databases. And this is probably very familiar to you. And in training data attribution, I like to think of these as thinking about these distributions just in a little bit of a different way. So you're still thinking about these adjacent databases, but instead you're trying to understand a model's behavior with and without an example. This sort of produces different distributions over the models, and you're trying to understand the differences between those distributions. And this output set, if you remember, we care about sort of specific predictions made by a model. And so I think of this output set as trying to reason about like the set of models that make this kind of prediction. And so, you know, and on this very high level, hand wavy argument, but you know, backed up by some of the research that has been, you know, derived and very related between the two. You know, I think of it as we both care about, you know, the same kinds of distributions, but we kind of are just looking at them in different ways. And so my hope is that someone here who thinks a lot about DP might decide or find that there are some theoretical tools or algorithms from DP that might be able to help improve or understand attribution a bit better. I also have a couple like concrete open questions that are less hand wavy than this that I'm not going to have time to get into, but if you can quickly read them and think they're interesting, you can see more discussion of them in the notes. Yeah, so I'm going to pause for a second, let you also, this is the papers that I talked about. These are also on the notes website, along with some other cool papers, including the tutorial that I mentioned earlier. Probably enough time. The next thing I want to talk about is data curation. This one's really interesting to me, but sort of before I really get into it, this is like the start of data curation, right? I think you're probably in differential privacy circles, you're probably used to seeing a different machine learning XKCD, but this one is just as good. In your machine learning systems, the sort of idea here is it's just a big pile of linear algebra. You feed in data and it spits out some answers. And this person on the left is asking this question, what if the answers are wrong? You know, you stir the pile until they start looking right. And you know, this is supposed to reflect like how people design architectures or optimizers and stuff like this in machine learning. But the thing that this XKCD omits is that there's also a really big pile of data. And this is also something that you can stir in order to make your machine learning do better. And that's really the high level picture of what data curation's goal is. And there's been some really like pretty nice results in data curation that doesn't care about privacy at all. So one that's really cool recently is data comp. So if you're familiar with Kaggle, the sort of goal of Kaggle is someone gives you a data set and you find the best model for that data set, you know, perform on the test set. The goal of data comp is sort of to flip that. So you give someone a model and like a training algorithm, and you give them the best data set to eventually end up with like good downstream performance. And so it's a question of how well you can select the right data points. And you know, I'm not going to get too much into it, but like some cool stuff that they can do is they can like give you a smaller model, like 10 times less compute, and you can end up with better downstream accuracy, you know, even if you're training on half as many examples or something. So like this is a field that's really sort of recently, I think, kicked off, at least in like non-private world. And I'm optimistic that maybe we can see some stuff in the private world as well. And one thing that's pretty cool in differential privacy is that we don't just have one data set often. Like often you have a sort of public data set and a private data set. And both of these things you can imagine stirring in order to make your final algorithm better. There is some really cool work on stirring the public data, including with sort of reference to the private data, and it's careful. I'm not going to get into that for now, but there's some papers that I referenced in the notes website. But today I just want to talk a little bit about stirring the private data and potential pitfalls that you can run into even if you try to do this. Right, I think as differential privacy people, we're not particularly accustomed to stirring our private data, to looking at it too intensely, and I think, you know, for good reason, right? Like often when you access and run stuff on your private data, you incur some privacy costs. That's sort of like the message of this paper is like, you know, data scientists, when they're doing data science, with differential privacy, it's more challenging. It's harder to do exploratory data analysis and so on. And thank you to our hosts. So right, like this isn't something that we're super accustomed to, and I'm going to kind of reinforce that a little right now by showing you something that can go wrong when you store your data in a very common way, but you store your private data, and things can go wrong. So data deduplication is super common. This is being done in sort of like basically all foundation models are training on deduplicated data of some sort. And it's like the part of the reason for this is actually because of training data memorization. So in a recent paper, we found that, for example, like diffusion models that are trained to output images from text will happily regurgitate training images that they've seen. So for an example here, this was the figure 1 in our paper. This training image of anagram Watts on the left is almost exactly reproduced on the right if you sort of just query the diffusion model for anagram Watts. But also in the paper, we talk about how this is a big problem, partly because of duplication in the training data set. So like this specific image here, like is actually contained in the training set over 100 times, at least sort of like near duplicate form. And when Stable Diffusion 2 like retrained without duplication, they found that memorization became a much worse, better problem. They had less memorization. And so deduplication is a strategy that's being used, but you have to be really careful if you're doing your own private data. And so I'm going to be talking a little bit about a piece of a paper that we wrote on what can go wrong there. So the deduplication algorithm that I'm going to be referencing is something like this. You find these little clusters and you remove everything in that cluster. That's one instantiation of deduplication. The specific details don't matter too much, but it's just what I'm going to be talking about. And what we're going to do is we're going to use deduplication to come up with a side channel attack on sort of your ultimate machine learning training. And we're going to do membership inference with this side channel attack. So we want to distinguish between these two worlds, non-member and member, where this one target example is contained or not. And the way we're going to do this is we're going to add this little gadget into the training set. And what this gadget looks like is this little triangle. And it's constructed such that in the non-member world, the sort of different elements of this gadget are not going to be sort of duplicates of each other. So you'll not identify these as duplicates. But in the member world, they'll be close enough to the individual member into the sort of target example that we want to target so that they end up being a sort of duplicate cluster. And so what happens is deduplication will identify this as the sort of a cluster of examples and remove it. And then what you can imagine is that after sort of training a machine learning algorithm, before deduplication, you're trying to distinguish between 3 and 4 copies essentially of some example, and that leads to some amount of membership inference vulnerability. But after deduplication, you end up trying to distinguish between 3 and 0 examples. So sort of in differential privacy speak, we've tripled the sensitivity. And in fact, if you sort of naively do differential privacy on top of this kind of thing, you can end up with privacy violations that exceed what differential privacy would allow because of deduplication. So we actually are in luck today because Yashi is going to be talking about a paper at 2:45 that addresses exactly this question. Different ways of sort of giving provable privacy even if you have non-private pre-processing. I'm not going to talk about that because you're going to hear about it later. But it's sort of nice that this is a thing, and my guess is that this is not the only sort of privacy relevant sort of data curation algorithm that exists. Actually, if you go to data comp and sort of look at it, there's a variety of different algorithms, and some of them might start to pop out at you. But like one thing that I'm really kind of curious about is data comp managed to reduce their sort of data set by a factor of 2. And this is also something that differential privacy people, we're very used to saying like collect as much data as you can because privacy gets better the more you can aggregate and like sort of that's. But I'm just curious if this is actually something that ever occurs in differential privacy, I haven't seen any papers one way or another whether sort of subsampling your private data set in a careful way can actually help after doing it the right way and making sure you don't come up with side channel effects as well. And then I do also want to re-highlight that there's some really cool work on sort of curating your public data set in a way that's sort of aware of your private data set, but only in a differentially private way. And so basically making sure you can stir your public data set pile is a cool thing to do. Also, if you've seen the ICML recent best paper on sort of critiquing the idea of public data sets, this is very relevant. You can see some stuff in the notes if you like. But I think that this is an area of machine learning that's really picked up recently. And I haven't seen so much in the differential privacy world, and I'm excited to see more. Great. So I want to close it out with a discussion of some privacy semantics, alternative privacy semantics that I've seen sort of talked about recently. And these are kind of more access control-y than sort of aggregate statistics-y. But I think that they're really interesting, and I think that maybe other people would find them interesting because they are often motivated with like privacy in mind. And so people might like to sort of look at these and think about what they sort of intersections or departures from differential privacy are. And I think my favorite of these is known as like retrieval augmented models. It's just like a really cool idea. So what you do in a retrieval augmented model is you take your model, and usually you'd sort of pass inputs and get outputs of this. But you augment this model with a big data set. You can think of this like relevant intranet like documents from your company intranet or something like this, or even the entire internet. And so when you receive an input to this model, you don't just directly provide an output. You first will sort of access the data store, find some relevant documents to answer this input or to respond to this input. And then you produce an output only sort of after having seen the data store. And so there's some like interesting properties of having this sort of mechanism in place, that are not quite differential privacy, but like privacy adjacent. Attribution, like I was talking about earlier, becomes pretty easy, at least for the data store part. You know exactly which sort of elements of the data store you have accessed and used in your response. And edit operations are very cheap. If you care about machine learning kinds of things, and the sort of information about somebody is entirely in the data store, it's very easy to delete that, or add it if you sort of that's for sort of if you add users to your system or something like this. This is sort of an abstract picture, but you might be familiar with this instance of retrieval augmented generation. If you use Google search ever, there's this thing called AI overview, which maybe you've seen, maybe you love it, maybe you hate it. But this is a retrieval augmented system, right? So the retrieval part of this is literally Google search, right? Like the data store is the internet, and the search mechanism is the sort of mechanism that's used in Google search. This model here is sort of bringing these sort of responses from search into the context of the model and producing outputs based off of them. And so the data store, sort of the elements from the data store that are accessed are here on the right. And this sort of model output is here on the left that uses these outputs. And you can see they even like tried to there's these little link things, and that's attribution being done, at least to some extent. Yeah. And this is also something that's sort of come up in the more, not exactly privacy, but like privacy adjacent literature. There's this paper called Silo Language Models. Their goal was more about understanding sort of legal risk, but it's using this retrieval sort of setup. And the way that they did this is the original model that you train, you have to get it from somewhere. They get it from like the public domain, permissively licensed data off of the internet. That they think is like more legit to train on, and so that's how they produce the model, and then they augment it with this stuff that's maybe less legit to train on, I'm not going to read the words there. I don't know how much Google would like that, but Yeah, but like this sort of allows you to do things like attribution for the sort of retrieved documents and stuff, which is just they argue is a maybe more clean way of doing it. They also talk about privacy here. You know, I'm not sort of totally sold on this being super relevant for privacy, but I would love to be proved wrong if anyone in the audience is interested in this kind of thing. The last thing I want to talk about is a paper that I thought was cool on a different type of privacy semantic that's still talking about like access control-y stuff, and it's sort of motivated by like an assistant who helps you fill out web forms. So the idea is, you know, I want to apply for like a Korean e-visa, right? And if I have an assistant in Google Chrome who wants to help me with that, you know, if the Korean passport or if the Korean visa application requires a passport number, the assistant should be able to reasonably say like, oh yeah, the passport number is required to get a visa, so you should put it in. But and similarly, if I'm registering for TPDP and the TPDP form asks for my email, you know, that's a reasonable thing to ask for so that I can, you know, get information about the TPDP conference for registration. But if the TPDP form asks for my passport number, you know, probably it shouldn't be saying, you know, okay, yeah, just use the passport number. TPDP is probably gonna need my passport number. So like there's something here that's not really captured by like differential privacy style notions. Of course, this isn't talking about aggregate data at all. But like there's something very contextual here. And in deciding why TPDP should not get access to your passport number and the Korean e-visa should. And there's a theory here known as contextual integrity that's, you know, I don't see as many papers on as differential privacy papers. And I'm not going to be able to speak too sophisticatedly about it. But sort of it's a way of reasoning about contextual privacy leakage. If Rachel Cummings is in the room, she knows a lot more about this than me if you have questions about it. The sort of thing that this paper ends up doing is they sort of try to incorporate contextual integrity into sort of a privacy, like a supervisor for these language models. And you know, so that you know, you're building on top of it with another language model. And I personally am not sure that I'll be using Google Chrome assistants to fill out forms in the near future. But you know, this is at least a problem that's worth looking into and trying to understand better. Yeah, my hope is that people in the audience might be interested enough in some of these different like approaches to doing something like privacy, but not exactly like aggregate statistics privacy. And my guess is there's a lot of overlap. And I hope that someone who wasn't aware of these before might find them interesting. And of course, there's going to be vulnerabilities in these kinds of systems that, you know, might parallel the membership inference attack and training data reconstruction attack like line of the differential privacy community, and that might be interesting as well. You know, language model supervisors on top of language model assistants might be a pretty straightforward thing to attack. I do also want to, I mentioned Rachel Cummings because she has this paper on combining like sort of contextual integrity and differential privacy guarantees. But other than that, yeah, these are just the other papers that I referenced. And with that, you know, I just would like to thank everybody for bearing with me. I appreciate everyone coming again, and I'm happy to take questions. And this slide's gonna be up for the entirety of the question time, in case you haven't managed to get the QR code yet.
All right, are there any questions? Yep. Going back to the first part of your talk, can you motivate data attribution? when is this useful?
Yeah, I think that a lot of people have cared about it for sort of debugging of models and stuff. It's also, you know, maybe useful for things like just understanding the value of different pieces of data if you're trying to sort of build a marketplace or something around data. Those are like some big uses.
Yeah, great talk. So, oh, sorry. So, like regarding this data attribution, I had this question that, like, how do you do attribution for things which are like could have depended on the entire data set? Like, if I ask you a physics, if I ask a physics question, and you require the knowledge of the entire physics textbook to be able to answer it. So then, how do we reason about data attribution in this kind of a setting?
Yeah, that's a good question. So in principle, like a data attribution technique could give you like one example, or a textbook might be like chunked over many different examples, and you should be able to point to all of those in principle. You know, there's other things that might be a lot more diffuse even than like a specific physics question. And I don't think that the sort of the training data attribution field has really like come up with a good answer for that problem yet. You know, maybe you could say something like, if it gets the correct answer, but you can't like, you don't have like a really strong prediction on any of these, maybe it's you just say it's diffuse or something. But like if you're thinking about these two distributions, one that's seen the textbook and one that hasn't, that's probably something that's going to be easier to measure than like seeing the textbook and maybe like imagining an entire different internet where you never have physics in it at all or something. So yeah, I think it's a good question, and I don't think the attribution field maybe has a perfect answer for it.
Yeah, I was curious about the attack on the deduplication. Like, why all the representatives in the duplicate cluster disappeared instead of like kind of leaving one behind?
Yeah. I mean, so in the paper we had like sort of 4 instances of deduplication that we were targeting, or that we sort of showed attacks on. Like, and so basically, you tell me a deduplication algorithm, and I can construct a sort of you know, side channel attack on it. So the specific attack that we were using, or the specific deduplication algorithm we were using, is sort of one which identifies approximate duplicates and sort of bunches them into a cluster. If you had a different instantiation, like it would likely be vulnerable to just a different attack.
I want to ask about the data store example, like scenario that you mentioned.
Yeah.
So data attribution is easy there because you are sure which example are used for the inference. But I'm wondering, because the data set is finite, and for example, you select a top K related example in the retrieval. So would it be possible that data that are not selected would influence the outcome in some way? Like in the sense that it forces some other example to be selected.
I see. So the sort of top K are not going to be influenced by anyone else, like because
if all adversary colluded, and they can like force themselves to be not related to the query in a way, so that some other K examples belonging to a private user must be selected.
Yeah, I guess this is possible, but like I guess it's imagining a scenario where the adversary had a relevant document and sort of and later decided they didn't want it to be relevant for a specific query, which I can see definitely a reason to look into this. Maybe if there's like lots of different queries you want to sort of simultaneously be attacking or not attacking. But I haven't sort of seen. It's a good question. Yeah, there's sort of other problems with like attribution in this sort of kind of model, which is you don't actually know what the model is using of the K sort of things you provide it. So I definitely think there's like still questions there to be answered if you're interested in attribution from this data store.
Thank you.
Yeah, thanks.
Hi, on this end.
Regarding the privacy semantics part of your talk, I was wondering if you could share some thoughts on privacy semantics in free-flowing text. How same fact, sensitive fact can be expressed in many, many different ways. And the same fact can be spread out among several token sequences living in the same document or multiple examples, multiple documents spanning the whole data set.
Yeah. Yeah, this is a really good question. And I think it's kind of getting at like what like privacy, you know, the kinds of things that we measure for privacy in the like language models are kind of a challenging fit maybe to sort of our traditional like membership inference kind of investigations. You know, I don't think I'm going to be able to say anything particularly so sophisticated here because it's just like everything is so messy. But like some things that I think are nice are like PII is like often, you know, uniquely identifying, right? And so if that exists in multiple documents, that's easier to sort of construct a privacy unit around. Or but yeah, you're right that like duplication is not just like exact duplication. It's like it can be duplicated in lots of very difficult to identify ways, and that can sort of impact privacy. I'm not going to have a perfect answer for you.
Hi, hi. Thanks for the nice talk. I had a question about deduplication as well. I was wondering if you have a sense of how we could maybe distinguish cases where there are duplicates because the data is actually less private. Maybe we don't need to be as worried about privacy because the person is a public figure. Maybe their image is replicated a lot and it's easy to even find through a Google search or something. And that might be, in my mind, the more common case of duplication versus, I mean, I wonder if you have a sense of how often that occurs versus cases where the duplication is actually somehow surprising or unexpected and is a case where like some really, you know, private data was on the web but got duplicated unintentionally, and then, you know, this attack is a real concern.
Yeah. Yeah. So this is a good question that's also, I think, complicated by just the internet being big and everything. I would say I maybe am a little bit skeptical of trying to sort of, if you think of every sort of data example that you have as a vector, of being able to find which ones are sort of like socially reasonably like duplicated and socially unreasonably duplicated. And I think maybe in your question you started getting at things that are like not thinking of it as a vector, but thinking of it as like a person who you might be able to find on Wikipedia or like through other different channels. And I'm maybe a little bit more optimistic about the sort of purely looking at a big database and trying to reason what's reasonable and not from a privacy perspective, or what's reasonably duplicated or not.
Yeah, I guess the diffusion example that you showed kind of, if you think of, I think some people have this mental model of these language models as being able to do retrieval almost like a search engine, and somebody who has their, you know, they want to advertise their book or something, they might actually want an exact replication. So maybe interesting to think of the net.
Yeah. Yeah, I mean, I'm still a little like skeptical that the right way to do this is like to encode it into maybe a definition, like a mathematical definition, rather than like asking the person or something like this. But maybe there's something there that I'm missing.